All right. Okay. I hope everybody joined. Well, that's not uh, important. So I didn't remove one of the slides. So context. When we deal with software, we deal with raw values like raw integers or raw strings, but like we almost always have to carry certain context around them. So if you're asking a user for an input, they give you a number, and it like you're asking for a number. You're asking what's your age, and then there is a certain uncertainty. Like they can give you a string, or they can give you a wrong number, or the number can be out of range, or they can give you a correct number. So you can have this happy path where everything is as expected, or you can have something that is you have to deal with something. Sometimes you have in the games, you for example have a certain context, and you have to react differently. Like if an NPC has multiple NPCs around, and you're doing like a swarming behavior, or if you don't, then you have to decide, okay, like what is the context? Like, do I have those bodies and we are doing swarming, or we are not doing swarming? So it like almost always you have to deal with something that goes beyond just a normal value. So then we kind of put in Haskell, we explicitly do that by wrapping values in certain context. And you've already experienced it with IO monad, with lists, or with maybe, that we have some values or some functions inside, and then we can either use it or do something on top of them. And then if you have values wrapped in some sort of context, normally you cannot say, add those two values together because they are already in the context. So you have to do a little bit of an extra work. The same as like an object-oriented programming. Like if you have certain values somewhere in a data structure, you have to use a getter, do something, and use a setter to put it back in the context, right? So objects are also contexts that hold values inside. And we don't directly operate on the person. We sort of say, okay, get me the age of the person and this one, and then do something and then put it back, right? So in OO, you're sort of doing it the same, but it's much more here in Rust and in Haskell that we're using those extra kind of contextual wrappings. So then we learned about functors, and functors are sort of mapping function over the value in the context, right? So we've learned about map or fmap, and there is this infix operator which we can use, and it basically says if I have a normal function operating on normal values, I can apply it to something which is inside a context, inside some box, right? So the fmap takes a normal function from A to B. We have a value A inside some kind of context, inside the functor, and then we're getting a new value B, again inside the functor, but this one is just a pure function from A to B, right? So if you have something inside an IO monad, you have like an int or string that you got from a user, it's inside an IO monad, it is a functor, and you can do transformation. You can say, okay, I'm gonna work on int, or I'm gonna work on string, and I'm gonna get something else. Like let's say maybe we're doing string to int conversion, like we're doing the parsing. And because we have those two values in the context, we kind of use the functor to apply that function inside, right? So you're sort of thinking about those structures. And then that's the basic one. And then we have a more complicated one where we say, okay, how about we have a function inside the context as well? So this one allows us to apply a function which is already wrapped in some context into the values that are in the context, right? So here it's sort of like in object-oriented programming, you would think, okay, I have a certain instance. The instance has certain behavior, and then I want to apply this behavior to a value in another instance, right? So you have this sort of a dual context on both sides. You have the context on the function side, and you have the context on the value side, right? It's pretty straightforward, I hope. So this one is different because I have two values again. I have the input value inside the context, I have the output value inside the context as well, but my function is not pure anymore. I don't have A to B, I have the function inside the context as well. So I'm kind of carrying the context for the function and for the values. So the input value is in the context and the output value is also in the context, right? It sounds really abstract, but if you think about it, like if you remember this is like really simple. Like I have just 5, I need to add 3 to it. I cannot say plus 3 to just 5 because this one is inside the context. So I have to have some trick, right? So the trick is the applicative, and I'm having now plus 3 inside the context, right? So this is, it feels kind of abstract, but we often use it in libraries. Like in JavaScript, we use it almost all the time. Like it has this sort of functional feel. And in many frameworks, we kind of use it, but we don't really think about it, that it's like we have something inside the context, right? So functor, one more time, A to B, and then applying it to values in context. So if I have the functor and I have the map, like if I have just 5 and I need to add 3 to it, I would say, yeah, just add 3, and then I have to use this to apply it to that value, right? All right. So now write a function. So if we have to write a function that adds 2 maybe ints, so like I obtained 2 values from a user and they can be wrong. So I have to parse it and then I can get nothing or I can get maybe ints. So if I have 2 maybe ints, how can I add them together? So the way we kind of doing it is we have, so add maybe ints. I have 2 maybe ints. So 2 maybe ints. And then my addition is doing addition and mapping the addition using the fmap to the first value and then to the second one, right? It's a little bit it's a little bit of a jump. So if we, yeah, let me show you with GHCI. So if you don't get something, the easiest way is to, let me, where is the terminal? New window. Here. So let's do GHCI. Okay. So I have two values. I have, let's say, right. So I will have A, which is just 3, and I will have B, which is just 5. So now I would like to add them together. If I say A plus B, that's not gonna work, right? Because the values are inside the context. That's obvious. But if I say, what will happen if I say plus, and then I fmap it, if I fmap it to A, what will happen? So if I do plus fmap to A is just 3. I will apply that function to plus 3. So to 3. So I will end up with plus 3, right? So let's try that. So let's say this is F. Yeah, I will not be able to display it. So if I try to display F, it will say, I don't know how to display functions, but if we oh, yeah. Come on, it's really tricky. Let's make it smaller and right. You still see it? Yeah. So if I ask for a type, tell me the type of f, it will say, okay, it's like a has to be a number because 3 is a number, and it's basically a function inside a context. So it's like just plus 3. So inside is a function. So our function is plus 3, and it is in the context of maybe, right? So if it's sort of like saying I have plus 3 just. So f is this now, right? A was just 3, and I applied this function inside A. So now it's like plus 3, and it's inside the context. So now I have a function which takes one argument inside the context, right? So because I have that, I can apply it to another value, which is 5, right? So now I can do plus 3 to 5, and I will end up with just 8, right? So this first part was achieved by me saying do plus apply, so f map it to A, and then the second part was achieved by me doing the applicative functor to B. So this one creates a function inside the context, and this one applies that function inside the context to B, right? So it's like a two-step process. And this pattern is very common. It's very common to start with a pure function, which takes more than one argument, map it to something, to value in the context, and then it creates as a partial function. This is a partial function, a carry, which has a first argument already substituted with 3, but plus needs a second argument, right? So now I have a function which needs one argument, and that one argument comes from this, right? So it always kind of scares students with the syntax. Like the syntax is a little bit foreign and it's a little bit unusual, but at the end of the day, it is quite straightforward in the sense that we sort of saying, okay, map me this pure function to this value in the context, and this function takes two arguments. So one argument is coming from here, and then this creates a partial function which is already in the context, and I'm applying it to my second argument, which is inside the context. And, it creates a function for us, add maybes, and then it will add two maybes together and will produce just 15, right? What will happen if one of them is nothing? Nothing will be returned, right? It composes nicely, so the unhappy path shortcuts, and it just produces nothing. What will happen if this function is not two arguments? The compiler will complain, because the compiler checks that all the slots are correctly arranged, right? Can this function be nothing? No, it cannot, because this is a pure function. It's not in the context yet, right? But applying this to this can result in nothing, right? So then if I have a nothing in the context, or I have context which is nothing, and I try to apply it to something, I get nothing, right? So then this kind of composes nicely, and it's quite straightforward. As I say, we often use it in libraries, but we don't realize it that's what we do. And that often happens in some languages like Rust when error handling happens and so on. So it sort of is composing this way, right? All right, so where applicative functions shine? For validation. Every time you need form validation, or you need to create a person from a JSON object, but the values like name, age, blah, 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 comes from JSON. And at each point you may have an error. You end up with nothing at the end, right? So with parsing, applying parsers sequentially, or with combining multiple effects in parallel. If you want to kind of do something and you don't care about the order, then you can combine it with applicative. We kind of, I showed it to you last time, where we had, let me put it up. So let's quit this. Yeah, so GATI. So I showed you this with two lists. So lists now are my context. And if I have two things to do, I have +10. I have to do +10. And for example, what else can we do? Multiply by 2. So I have to do two things and I have two values. So I have 2 and 10. I can do it in parallel using the applicative. I forgot the plus and single brackets. So then it kind of does +10 to 2, +10 to 10. So I have 12, 20, and then multiply by 2 and multiply by 2. I get 4 and 20, right? So it's doing like 4 things or 2 things on 2 values concurrently, and then it's sort of giving me the results at the end inside the context. So for this, you can use applicatives as well. So combining multiple effects in parallel and then applying parsers. So this is typically the pattern is if you are parsing like the JSON, let's say, and you're getting like the name, an age, and an ID, let's say. So let's say we have to create a person, and the person takes 3 arguments, an ID, name, and age, right? So then if you want to create a person, you would say person, and then you would say ID is, for example, 23, Mariusz as a string, and then you would say, what's the age? Like, I don't know, 34. So then, so you have an ID, name, and the weight or something, right? So that's how you create a person. You kind of call this function and pass 3 arguments, right? So now if those 3 arguments are coming from JSON and they can fail because you have to do parsing and you have to get those values, and one of them becomes like maybe, like all of them are like maybe ID, maybe name, maybe whatever, then what you can do is you can do this. You can say, okay, I can get a maybe person. So the type of this would be maybe person. But what you do, you would say, okay, apply, so map this function to my parse ID, right? So parse ID should give you a maybe ID, right? And then this maybe ID is combined with person, and then this one is combined with parse name, and then this one is combined with parse weight or something, right? So each of those parsing ones can produce nothing. They kind of are developing like a value. So I have value, 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 value in the context, value in the context, value in the context. I have a function which needs 3 arguments. So then if I apply it to here, now I have a partial function which needs 2 arguments. And I'm combined with this, I create a new function which just needs 1 argument, and then combined with this, it creates me a maybe person, right? It's a very typical pattern for parsing or for valid form validation or whatever, right? And it is kind of a nicely expressed, starting with a pure function. Like this one is not in the context, like person just creates a person. So this is a pure function, which takes 3 arguments. But then I'm passing those arguments using the applicative, right? So once you get it, then you will start recognizing it that, oh yeah, I've been using it in other frameworks or other languages. And frameworks which feel nice to use usually follow something like this, right? So this is great. So we got to applicatives. We covered that before. And now we go even one step further, right? So this one step further is we were working on functions which we apply to values. And now we say, and the context was kind of static. Like the context was like not like an object-oriented way that you have some state inside the object. It was just, okay, it's either nothing or a value. or it's a left side or right side, and that's it. Like there is not much you can kind of deal with. There is no really a lot of state. It's sort of just a little bit simplistic. So what if we want to carry a little bit more information, like in the context? What if it is sort of like an object which carries a state inside, right? And depending on the state, we do certain things differently, right? So that's where monads come in. So monads are, they kind of extend applicatives, and they allow your computation to depend on the previous result, right? So in applicative, it does depend, but it is like, if you look at this, if parsing name fails, like if the user entered like invalid name, right? So then what happens is this creates a partial function, and then this partial function hits the nothing, and then the computation stops. Like we go into the unhappy path. That's it, right? You cannot say, oh yeah, if it was this error, do this. If it was this error, do this, whatever, right? It just goes to the unhappy path, and that carries over, right? If we have some error handling and we use either instead of, so instead of maybe we want to have either, right? So we have either person, we have either some form of, let's say we use a string as an error. So we have either we are on the left-hand side and we have an error and it's a string, or we get a person, right? So then those guys have to return me a value, like real value on the right-hand side, or give me some error on the left. So let's say this one gave me a value and this one gives me an error. So then my computation goes, hits the left side, goes to the left side, and that's it, right? I cannot like change what I'm doing next. I'm kind of on rails, and I have to do what I already planned, right? I cannot change my mind. But with monads, you can change your mind. You can say, okay, I have certain context, and then depending on the context, I can do this next thing in a different way, right? So this is what like imperative programming does with objects. You are calling something on the object, and the function checks, okay, what is my state? What should I do? Is my state allowing me to do this or this? Usually you use if statement, or you're doing some sort of logic, right? So here is the same. It allows us to compose computations depending on the previous values and using that information. And it is a little bit different to the previous ones. So we have a value in the context, and then we bind that value in the context to a function which takes a normal value and produces a new value in the context. So like we have to have a value in the context, and then a function which takes a normal value, not in any context, like a pure value, and produces a new value in the context. And then this function is applied to this context, and then it generates this new value in the context. So let's say A is an int, and we're getting a string. So if we say, okay, we have this sort of int in the context, and then we have int to string in the context, this one creates like the context for us. And then we apply this to create the final thing. So it's sort of, it takes some time, but it it's like chaining computations. You have to do something. When you do something, you have some values, which are your pure values, and you have certain context. And then you want to do the next thing depending not only on the value, but also on the context, right? Maybe is a monad as well. So you can think of it as like monadic computations, but it's very simple in terms of carrying context, because the context is like binary. It's either nothing or something. Either is also a monad, so you can also do that with either to get the intuitions, but the context is quite small, like it's just left or right. So if you want more, if you want this server object-oriented feel, then you have to put more in the context. You have to keep carrying a little bit of extra information inside the context. So this is like, for example, a safe division. So I have two ints, and I want to divide one by the other, right? And normally, if you divide by 0, you get a panic, you get an exception. And we learned that you should not use panics. So let's create a simple safe division, which says, okay, if it's a normal numbers, I will just get the result, right? But if I try to divide by 0, I will get nothing. So I don't get a panic, I just get nothing, right? So then if I have my calculate function, and I want to calculate what is this one divided by this one, then I can do this bind thing. So this operator is called bind, and it binds a normal value, a value in the context, to a function which takes a normal value and creates a value in the context. And then it will produce me a new value. So then I can bind this new value to the new computation, because you can see how the chain will work. So I have value bound to function, produces me a value, which can be bound to function, which produces me a value, and so on, right? So it's sort of, previously we started with function bound to a value, and at some point it will finish because I ran out of arguments. This one is like value to function creates a value, to function creates a value, to function, and so on. So this one can go forever, right? So this one is a little bit tricky to read because it uses those lambda functions. But this can be rewritten with do notation, and then it really reads like an imperative program, right? So let's try it. So we basically here what we're doing is we're saying, okay, I get two values in the context, and then I'm bounding. So I'm bounding the first value in the context, mx, to a function which takes normal x and produces a function. And the function it produces is, again, a bound which takes a value in the context and takes a normal value, which produces this function. And because I'm already nested and I already got x and y from mx and my, I can do this safe division. Because the safe division, the safe division takes normal value and normal value, right? But it has to produce something in the context. So my safe division produces something in the context, and then I got those two by this bind operator. When you initially look at it, it's like, oh yeah, that's sort of so complicated. But if you unpack it, I can show you how it will look. How it will look here. So we have two values in the context, mx and my, right? So I have mx. Let's. So I have my a value, which is like mx, and this is of type maybe int, and b, let's call it y. No. Let's keep it this way. So I have mx and I have my, and it's also of maybe int. And now I want to have this function calculate, which takes those two maybe ints, right? So it takes mx and my, and it produces the safe division. Remember the safe division implementation, right? It's this one. So what I can do is I can basically say do, and then I will say, give me x, and you use this notation. So it's the less than and dash. So it's like, because of my fonts, it kind of rubs. So it's like this one and dash together, right? And then you say mx, and then you say y, give me the value from my, and do safe division on x and y. This is exactly the same code, which is this one. This code and this code are exactly the same. It's just that this one uses do notation and it's like easier to read and kind of nicer to work with, right? And it is kind of encouraged and it feels like imperative code, right? So what we're doing here, we're saying, get me the X out of the context. I don't want the context. I want just to give me X, a pure value. That's what this one does. And then give me the Y from inside the context. And then do the safe division, right? What will happen if this one is nothing? So like we have the value in the context, but we're saying, get me a value out of the context, and we're doing the maybe thing. So we're using maybes. So this is maybe int and maybe int. One of them can be nothing, right? So what will happen if this one asks for nothing? It will shortcut. It will go to the unhappy path, right? So it will say, okay, we have to return nothing because we cannot do the next thing because we are kind of stuck, right? So if one of them returns nothing, this call will never happen, and this function will return nothing. It will kind of shortcut the unhappy path, right? So if you see it like this, it kind of makes perfect sense. If you see it like this, it feels a little bit too much functional flavor, right? Because we're doing those two lambdas, two inside functions, which extract the x from us, from mx, and extract y for us from my. But you don't have to use this. You don't have to use this. Although sometimes it makes more sense to use the byte operator, and it like reads nicely. But you can do this instead. And then it's sort of a little bit more, easier to follow and easier to understand what's going on. You don't use equals because you're not kind of doing equality, you're doing the extraction. So this left arrow is like the unwrapping of the context. So there also one important point. This do operates within a single context. So if my calculate function takes maybe int, and produces what? It produces maybe int, right? So my do operates within the context of the return type. So it cannot return either. It cannot create any new context. It has to be the same context that this one says it is. So each of those arrows has to be kind of linked to whatever type is the return type of what I'm doing inside the do. So do is doing something which has to return this. And if it has to return this, those arrows are kind of enforcing this thing here. So if you, for example, passed, if you passed, like, let's say we have the second one is not maybe int, but this one is like either string, so we have some sort of error on the left, string or int, then this one will not work because this arrow applies to either, but this do applies to maybe. So now you have a problem. This arrow will not sort of compute, right? Because then you don't know what to do. Like if you get left side or right side, like you cannot shortcut, right? So if you want the arrow to work, you would have to make this either, and this either, and then those would all work because they kind of match. But if one of them don't match, then you cannot do this. So then for this case, you have to kind of hard code some logic of what you're doing when you have this extra wrapping, right? And this comes into play when you have more complicated computations and you have certain layers. So you're like saying, I'm kind of getting those maybes, but then I'm doing something with the maybes and I kind of end up with an error or not. And then you maybe want to wrap it like the initial computations are kind of wrapped inside maybes, but your like more complicated thing is wrapped in either. And you have this chain and you have these layers of what is the context here and what is the context there. And then you have this kind of a lift operator So you have lift, which lifts you from one context to the other, or kind of drops you to the other one. And then by lifting or dropping, you can use the arrow again. So because you can kind of switch the context. It's a little bit abstract, but again, it kind of organizes your computation in a more formal and strict way, and you can reason about it. Like we doing similar things in object-oriented programming, but it's very ad hoc. We like very loose. Like we say, oh yeah, now in this context, now in this context, and we don't kind of care. This one enforces us to be actually organized, and it enforces the compiler to check that everything is actually correct. And it can parallelize things for us as well, because it knows what's going on. So it is much more powerful, but it requires a little bit of extra machinery of thinking about it, such that you can organize it well. But you can organize it well, and as I say, you can kind of organize the do nestings, and you can organize certain things in such a way that it actually feels very nice. So I hope this kind of makes sense, and I hope it's sort of this calculate with the use of this context kind of helps you. Like it doesn't like what we achieved, we could achieve with applicative, right? We don't have to use monads to achieve the same result, because this can be composed using applicatives with the shortcut to nothing. But there are more complicated contexts, and we will have today, we will do like an exercise where you have to carry a stack. You have to carry like a data structure in your context through all your computations such that you have the latest resulting value, right? And in this case, you have to use monads, because applicative, to do the same with applicative, you have to carry that stack like explicitly in all your pure functions, which makes the code a little bit more complicated. So you will see, like I have some examples after, where the monads are better because they make your code sort of much simpler. All right, so when monads shine, input, output, obviously, everywhere you're doing I/O, you have to use monads because I/O is a monad. State management. So every time you have a state, and that's pretty much every time. Like every time we're doing something, we have to process state, and we have to, do something with the state. So state management, monads are really good for this. Error handling, like propagation of errors. So an error recovery, right? So with either or with maybe, if there is an error, you kind of drop to nothing, right? But then the caller has to do something, like the caller has to deal with it. And the caller may have a more nuanced, like handling for I/O errors or user errors or whatever. You're doing it in cloud, you have different types of errors. Like you either have something on the client side, you're dealing with it differently, and you have your internal database problem, you're dealing with that differently as well, right? So depending on the nature of the error, you may decide to go like this way or this way or this way. And then either and maybe are not powerful enough. You have a little bit more powerful mechanism. So then monads are the mechanism that you need to use. And then obviously for asynchronous programming and doing like asynchronous and concurrent operations, that is super nice as well. So you will see monads sometimes, and you will see monads in other programming languages, like in Rust, which are built into the language to do those things, to kind of help with error handling or propagation of errors, or to, in some Rust libraries, to do asynchronous programming. So you will kind of see that. You will not see it for input-output, because in imperative programming, we sort of don't care so strictly about the state. So we say, yeah, you can print to the screen every time you want, right? But in Haskell, you can't. You have to say, no, I'm kind of violating the purity now, and I'm doing I/O, right? So you have a pure core, and then you have some sort of I/O layer kind of on top. And the benefit of doing this way is that with this pure core, you can do very strict testing. You can really easily like unit test everything, right? With I/O, it's not that easy. All right, so then repeat. Functor, apply normal function to value in the context. Applicative, apply function in the context to a value in the context. And then monads, sequence computations. We're doing more complicated things. We're sequencing certain operations and carrying the state along the way. So apply a function in context to a value in context and carry the state between the contexts, right? And the state can change. So the state is more than binary. It's more than just something or nothing. It's like, yeah, I have just something, but with extra information, right? With some extra things that I can reason about. And this one is sort of a more complicated box. Wow, 15 questions. I didn't know we have so many quiz questions. All right, so let's go with the quiz then. So let's do 2 or 3 questions and we'll have a break. So let's see how it goes. Okay, so this one tests whether you paid attention. So when we usually use applicatives? So every time you have to do it, you may think, yeah, I probably should use applicative here. It kind of makes sense. Damn it. All right. Input output, monads. Definitely monads. Asynchronous programming, monads. State management, monads. Form validation, right? Applicative. Applicative is enough. All right, let's see. Okay, interesting question. Very good. So that's true. If you have a monad, you can always use the apply operator on every monad, but not every applicative is a monad. Some are, but some are not. So it kind of works this way. So if you have a monad, you can always use the and star apply operator. But if you have an applicative, sometimes you can use bind, sometimes you cannot. It depends whether the applicative follows the monadic laws or not. Very nice. So let's see. Okay, what will happen? Very good. Normal value. Value in the context. Value in the context, but value is missing. Just the context. And then panic or error. Normal value. Functor. Applicative. Functor. Applicative. Panic. Fmap. All right. So that was really good. What will happen now? Reading the code. So error, perfect, very nice. Why? Why that does not compile? Because we have a function in the context. We have a function which takes one argument inside the context, and we're trying to use fmap. And fmap takes a function without the context, right? It has to be pure function, something to something. So that does not compile. All right, one more. How about this one? Same, perfect, very nice. Same reason. We have a pure function, but we're trying to apply pure function to something inside a context. And apply needs a function in the context, not a pure function, right? So that's the difference between apply and fmap. So this maps a normal function to something in the context, and this one applies a function in the context to something in the context. So this one does not compile. Very nice. One more, and we have a break. All right, perfect. So this is a good code. Function in the context applied to value in the context. We do +5 to +2 to 3, and then we get just 8. If one of the sites is nothing, the result of application of apply is nothing. It's shortcuts. Fmap functor, apply applicative. All right, so let's have a break. 5 minutes or 10 minutes? Fair enough. 10 minutes then. All right. And I will push the lab for today. All right. So far so good. We have some movement. Pretty good. So let's continue. Question 7. So we're halfway through. All right. So we have fmap, apply, and pure. Where do we usually use them? Fmap, apply, and pure. Applicative functors. With monads, we need bind. So we need something slightly different here. Is fmap part of applicative? So pure and apply are for sure part of applicative, but fmap is part of what? Of functor. But applicative is a functor, is an applicative functor. So fmap is sort of by inheritance part of applicative functor as well, right? All right, so each applicative, every applicative is a functor. There is no applicative which is not a functor. It is actually called applicative functor. All right, 8. Okay, so here we have the bind and return. Return is kind of confusing in Haskell because it's not what you think it is. Like, it is not what it is in imperative programming. It is something else. But it is all about monads, yes. So the bind operator and return are all about monads. Okay, so now you'll have to read code. I hope it will be not too small. So which line of code is correct? So you kind of need to remember, like it is useful to memorize some of the patterns and some of the signatures, okay? So bind, we need to have a value in the context, and we need to have a function which takes a normal value, which this one does, which is correct, and produces value in the context. This one doesn't. It's a pure function. It takes an integer and produces integer, right? So this one has a correct structure. It's just that this function doesn't fit because bind needs value in the context and the function which takes a normal value and produces value in the context, right? So this one fits because this one will produce, like, this one takes a normal value, which is correct, and produces me a value in the context, which returned us. And that's what we're doing here, right? So he's saying, do plus 20 to whatever it's passed. So do plus 20 on 10 and wrap the result in the context. So this function is good. So that's why there is a difference between this one and this one, because the structure is correct. It's just that this function doesn't return me value in the context. This one does. And that's what return is. Return wraps a normal value and returns a monadic context. It's kind of the equivalent of pure for applicatives, right? So this one is good. This one is wrong because it has the opposite. Like, we need the value in the context on the left-hand side and the function on the right-hand side. So the function is good, the value is good, it's just that they are mixed up. They should be on the other sides. So this one is wrong. Then this one is good because it's exactly the same metaphor as this one. It's just that the wrapping is done by pure, by the applicative instead of the monad. But because maybe is an applicative and the monad, the pure wraps it in the maybe, and then it is a monadic context. So we basically are fine. So we can, for maybe, we can either use pure or return, and it will work the same way. Because pure, return in maybe int is actually pure. It calls pure to achieve the wrapping, right? So if I have value if I have value 20 and I want to make it into maybe, I say pure 20, and then I will have it wrapped, right? So this one is good as well. It's exactly for the same reason as this one is good. And then this one is bad for the same reason this one is bad, because the arguments are wrong order, right? So if you memorize that bind takes a value in the context and the function which needs to produce a value in the context, but the initial value has to be pure, like the normal, then you can kind of read it relatively fast. If you don't memorize it, it is kind of complicated. So there are small things that you kind of need to memorize. All right, another one. Okay, so after this discussion, this one should be easy. This one should be straightforward. So perfect. Very nice. That's really good. All right. So next slide. You're getting the pattern. Oh, come on, start. So now you have to mark what is a monadic value. So in this expression, you don't calculate what's the output. You calculate what is in this expression a monadic value. So a monadic value is just 10. So this one is a monadic value. It has to be the left-hand side of bind. So left-hand side of bind is always a monadic value because that's what bind takes. It takes a monadic value. So this one, like 100% sure. Those two are normal values. They are not monadic. They are just in numbers. Like it's just a primitive value, right? So they don't have any context around them. So those two normal values. And then this one is not a monadic value because it is a function. It's a function which takes one argument, right? It's a function which takes one argument and produces a monadic value. But in itself, it's not a monadic value. It is a function. This one is also a function. And then this one, same as this one, is like a monadic value. It's just 30. So if you calculate that expression, the calculation of this expression will be just 30. And then just 30 is a monadic value. So the return, like the outcome of doing this, is a monadic value, right? So if we go back, let me go back to a monad. Remember this? Monadic value, monadic function, normal value, monadic value, monadic value. So the bind on the left-hand side has monadic value, and as a result, the outcome is a monadic value. The right-hand side of bind is we call it monadic function, because it takes a normal value and produces monadic value, right? All right. So that one was a little bit harder than expected. Code reviews. This one, yeah, this one was a little bit complicated. So value is a value. A monadic value is value inside a context. Those are, they don't have context. Those two have context. Those are functions. Functions are not values. And left-hand side is a value. The outcome of this is a value. Right-hand side is a function. Okay. 3 to go. So what is a monadic function in this expression? Yeah, now that should be easy. After we just talked about it. Yeah, pretty good. So this one is a definitely monadic function, and this one is definitely a monadic function as well. This one is not a function. This one doesn't take any arguments, doesn't like it, it's a value, right? So that's why this is not a monadic function. If I cut out 10, if I say just, would that be a monadic function? Is just a monadic function? So let's have a look. Yeah. Okay, we are recording, that's good. So if I go back here and I quit and I clear and I go to GHCI and I ask, okay, tell me what is just. That kind of looks like a monadic function. It takes a normal value and produces to me a value inside a context, right? Remember the definition of the monadic function, which is like this. It takes a value and produces something in the context. So that fits the pattern. So just is a monadic function. Same if you ask about return, it will show you kind of the same, but it sort of says M is actually a monad, right? Here, it like just is like a specific case. This one is a generic function. It doesn't have actual type. It has a type class. It says, okay, M has to be a monad. This one is a concrete function, not generic, which already has filled in into the maybe type, right? You understand the generic types and like concrete types, right? You understand the difference between a generic type and a concrete type, or not? So in many languages, including C++, we can write a function which is like a template, which takes a type as a parameter. And then we can, for example, say, like let's say we have some sort of storage, and that storage does not have a type yet, but if you instantiate it, it will have a concrete type. So you can say we have this generic storage for stack, which is like a stack-like a data structure, but it does not have a type yet. But then we instantiate it, and then we say this stack is for ints, it stores integers, or this stack is for strings, and it stores strings. So the concrete type has a well-defined like a data structure and type already built in. And the generic one says, we don't know yet. The user, the programmer has to define the type when it instantiates it, right? So if I have a function f, which takes two things, and it returns this in Haskell, right? So I have a function f, which returns the sum. This is a generic function because I don't say if a and b are integers or floats, right? So this one, if it is if it is of type A, and I can use a type class, because for plus, I have to say those things have to be numbers, right? So I have to say name num. So I say this function is generic. It takes any numbers, and it is from A to A, right? And A is any number. So this one is a generic function. Oh, crap. Yeah, so I will not press enter, which is kind of unfortunate because I want to write and then new line. But so memorize it. So FA to B, this one is a generic function, right? And now if I say, actually, it is not a generic number, it is an int to int. Now it is a concrete function. It's kind of instantiated for ints only, right? It's not generic anymore. So generic means it takes type as a parameter, and concrete takes values as parameters, right? So in Haskell, we often do generic functions because it's super easy. In C++, to make a generic function, you have to use templates, and you have to be a little bit more advanced to kind of use this type of machinery, but you can also do that. And even in Golang, you can do generic functions. Golang also have generics, and you can define a function which doesn't have a type yet. You're specifying the type later when you instantiate the function, right? So in Golang, you also have generics. But so in this case, as we were discussing with the return and pure and just, so again, if I ask about type of return, this one says it's a generic function. It doesn't have, A doesn't have a type yet. Lower A is just a type variable. It takes a type later, but we don't know what A type is, right? We only know that it has to produce monad. So M has to be a monad, but what A is, it doesn't have any constraints. A can be any type, like there is no constraints at all. And then for the type of just, we see that it is from any type to any type, but this A and this A must match. And then there is a monad, which is the maybe. So it's not a generic M, small m, it's actual concrete type. Types in Haskell always have capital letters, and variables have small letters. So if we ask for pure, we'll see the same, that it's the same as return, that it takes a normal value and produces me a value in the context, but the context has to be an applicative functor, and it's F, right? So it has a constraint, and you can do constraints in, usually when you have generic programming, you have some way of expressing what the constraint on the type is. And we will have generic programming in Rust as well. And we do have it a lot in Haskell. We're using it like almost all the time. And as I said, you can use it in Golang and you can use it in C++. All right, so just would be a monadic function, but just 10 is not anymore. This is just a value. All right, so let's move on. All right, a little bit of small reshuffling, but you seem to be doing pretty well. When do we use pure? It's an open question. When would you use pure? Yeah. So when using monads, but when using monads, you actually use a return. So the equivalent of pure for monads is return. Pure is for applicatives. So when using applicatives, but you can use it for monads too. Yeah, the word map is probably a little bit confusing. So you probably should use a different word than map, like convert pure values to monads or applicatives or something like that, like transform, because mapping means you actually exerting some behavior. So we're not technically mapping, we're just converting one value to another value. We're not like kind of applying or mapping any behavior on top of it. So let's have a look quickly with pure. So remember this. Remember this person map to like parse name and then applicative parse ID kind of situation. Remember that form for validation? So we used person, which was mapped to this and blah, blah, blah. What we could do instead, so this is fine. I mean, this would work, but you could say, I kind of like a little bit more. I'm like, I have OCD and I want it to be a little bit like purer. So what you could do is you could say pure person, and then you can directly do this to parse name, right? That would also work nicely because now you wrap the function inside the context, and now you're just applying with applicatives, right? You don't mapping anything, you're just doing, what was the other one, parse ID? Like you just combining it now with applicatives, right? You cannot combine the pure function with applicative, with this apply, because then the compiler would complain. But if you wrap it in the context, then you can, because it's already in the context, right? All right. So when do we use return? Yeah, we use return with monads when we want to wrap. Yeah, it's a generic pure. It's sort of an equivalent of pure for applicatives. Yeah, so yeah, you're getting the idea. All right, 2 more questions. All right. Very nice. Very nice. So we're mapping the function to just 10. We're getting just plus 10 as a result. So it's a function in the context. And then we're applying it to that value in the context. And we get the just 30 as the result. Very nice. Is this code correct? This is a completely different question. It has nothing to do with applicatives. We just like looking at the code and checking if the code is correct. So like, think about it. Is this code correct? You have the answer in your head? Then answer. All right, so let's see. So yeah, kind of 50-50. Let's go back. So the people who said that this code is not correct, why? Why it will fail? So this line, nothing incorrect in this line, okay? This line, is there something wrong with this declaration? No, it is fine. So we declaring a student type with the type constructor. It takes 2 arguments, like string and an int. Fine. How about this one? It creates a handle to an instance of a student with name and age. Also correct. So those 2 lines are correct. How about this line? What this one will print? It will try to print M, but is M printable? No, it's not, because we didn't derive the show, right? So it will fail here because our type did not derive the show, like it doesn't know how to print stuff. So to be able to print, we have to make our type printable, and it is not printable at the moment, right? So this line will fail. So why? Because of the meta classes. The meta class was missing, right? So the show implementation was missing. So for example, here we have the same. We're declaring a person type with name and age, and we are deriving show. So we're saying, yeah, the compiler, implement, show meta class on top of our type such that we will be able to do print. Right? So now this one will work fine, and the print will work fine. Make sense? So what are meta classes? What is this kind of magic show here? So it's kind of interesting because we have normal types like integer, bool, person. Those are normal types. Then we have generic types like numbers or, I don't know, things that are showable and so on. And we need to have an ability to express a constraint, like what is that type for, what that type can do, right? So for example, we have constraints in a form of specifying a certain interface. Like you may say, if I have numbers, then numbers are able to be added together, right? So what we could do is we could go back here. CI, and we can say, okay, tell me about numbers, and then rep. So tell me about numbers. And then it says, oh, yeah, numbers is like a constraint. It's not a normal type. It's a kind of a constraint on a type, which means the type which fulfills that constraint has plus, minus, multiply, negative, absolute, signum, and so on. It has certain operations. It's sort of like an interface, right? So it says, if a type has all those implemented, then you will have an instance of that constraint, of that class type. And then the instances is double, float, int, integer, and so on, right? Those are concrete instantiation of that constraint, which already have that implemented. And you can implement it yourself. You can have your own type, which implements a number, which follows this as well, right? So it's like an additional layer on top of types, which allows you to specify what your type should have, what properties it should have. I mean, you can think about it as a sort of an interface or abstract class in object-oriented programming, which defines what it has to have. And then you have certain instantiations. You have certain types which are implementing that interface, right? It's just that in Go, in Haskell, it is called meta classes, and then it is in Rust it is called traits, but the mechanism is kind of similar, right? And in C++ it's called constraints. You have certain template language for expressing like generic operations, and then you have certain constraints which say what those variables have to be able to instantiate it, right? All right. So 56, we have to change the location. Let me see, there is a question. Yeah, so Nick kind of recognized that it's missing deriving show. Yes, correct answer. So I will stop here. We will kind of pack up and go to S building, and we will talk a little bit about debugging. So it's a bit of a rant, so I hope it will kind of go quite fast. But I will show you some techniques of, or I will try to convince you that debugging Haskell is a bad idea, basically. All right, so let's go to S then. Yeah, online people, a short walk to a different building